Hello everyone. Today we're going to be talking about section 2.8 in our math analysis textbook, which is all about one-to-one functions and their inverses. So first of all, we're going to have to define what one-to-one means. And I've written the definition right out of our book. A function with domain A, so we have a function, so it passes that vertical line test. With domain A is called one-to-one, so we can write it out as one-to-one, or sometimes we'll see this one-to-one shorter notation function. If there are no two elements in your domain have the same image. So in other words, no two values will get mapped to the same value. Another way to write that mathematically is f of x1 does not equal f of x2 whenever x1 does not equal x2, which kind of doesn't sound the same, but it is. So kind of explain what this means. Like we just said that no two x values map to the same thing. In other words, if you have two different values, x1 and x2, and you map them, these two guys are different, these two have to be different. Okay, so if these guys are different, their y values are different. So no x value will map to the same y value. Okay, so if we had our pictures from before, we don't have this sort of thing going on. We don't have two values mapping to the same thing. This one is not one-to-one. All right. How can we tell? Well, it's easiest to tell by the graphs, and it just takes some time. But we use the horizontal line test to determine this. Horizontal line test. So similar to the vertical line test, for functions, we have a horizontal line test for one-to-oneness. So if we passed horizontal lines through it, we're not going to have it crossing twice, because if it crossed twice, that meant that two x values went to the same thing, and there would not be a one-to-one function. Looking at some pieces, and this is where you start having to have a knowledge of the functions that we work with and what they look like, and so forth. So looking at y equals x cubed, is this one-to-one? So I would kind of think, what does x cubed look like? So this is one that should be starting to get into my memory banks, and it's that kind of S-looking thing that snakes up. Looks like that. It does pass the horizontal line test. In fact, every value you put in there has its unique outcome. So every input has a unique output. So this one is, yes, it is one-to-one. How about y equals x squared? Is that one-to-one? Well, x squared is our favorite friend, the parabola, with vertex at the origin. That one, horizontal line test, passes two places, so this one is not one-to-one. In other words, if you take a positive 2 and a negative 2, we know that they both would map to the number 4. Okay. Sometimes we will still look at these when we go to the next step, but we will restrict where we look. So we'll look at a piece that is one-to-one. So we'll maybe just look at that part, so we can say this portion of that x squared function is one-to-one, does pass that horizontal line test. So then we can look at what our next step is. So sometimes we can say, is this one? No, but if we do y equals x squared, where we're just looking such that x is an element of this region, so we're looking at just the positives, then that answer becomes yes. So if we restrict domains, sometimes we can get them to be one-to-one. All right. If we have a one-to-one function, we can look at a new piece. So let's say we have let f be a one-to-one function. So it passes both the vertical line test because it's a function and the horizontal line test because it is one-to-one. And it's got a domain of A and it's got a range of B. Then its inverse function. Now the inverse function is denoted f with this little -1 up there, and I'm going to talk more about that in a second. It will have a domain of B and a range of A. Notice the domains and the ranges flip. It is defined by f inverse of y is equal to x if and only if. This is read, this double arrow is read as if and only if. So it is something that goes both directions. So if f inverse of 2 is equal to 1, that means f of 1 is equal to 2. And vice versa. It goes back the other way too. If f of 5 is equal to 7, f inverse of 7 will be equal to 5. One thing to note here is that our x's and our y's are being flip-flopped. And that's how I like to think of it when we talk about the inverse, is that the x and the y change roles. And this has to be true for every y that's in that B, that's in the domain of the inverse. A little bit about this notation, and I'm going to make this a big note. This thing does not mean 1 over f. Okay? It is not an exponent. Not an exponent. And this is where some of Sir Isaac Newton's notation becomes a little bit confusing. So he liked it, so it has stuck around. But it does cause issues with some students. We just have to get over that idea that this does not mean 1 over. If you wanted a function to be 1 over, you would actually write it to the negative first power. By putting that -1 inside by that f, it does tell us that we are talking about the inverse function. This gets very confusing when we get into the trig functions, but we will try to keep it all straight. Okay, so let's look at just a few examples before I stop this video and go to another one. So let's say if we had f of 5 equal to 7, what this means, so if f is 1-to-1, then it has an inverse. Whoops, if f, put an f in there, is 1-to-1, then it'll have an inverse because it is 1-to-1. And we can say then f inverse of 7 takes us back to the 5. If f of 3 is equal to 9, then f inverse of 9 is equal to 3. If f inverse of 2 is equal to 1, that meant that f of 1 is equal to 2. So kind of having to get used to the fact they just kind of switch each other around. Okay. One last note. What if I did f of f inverse of something? Well, the thing to kind of remember is these kind of undo itself. So think about taking f of this. Going back up here, if I did f of this, I'd be taking f of f inverse. Well, that would be f of 5, which is going to give me that 7. If I did f inverse of 9, so f inverse of 9 is 3, so I'd be doing f of 3, which is 9. I will get the x value, whatever was in here. And this is true for all x in the domain of F inverse, which is the range, kind of reminding us, range of F. So kind of keeping track of all that stuff. We can do the reverse as well. You know, apply F first, and then I do the inverse to it, it's going to take me back. This also gives me X. And this is true for all X in the domain of F. And the reason I easily knew it was the domain of F is because that's what I have to do first. Here I have to apply F inverse first, so that means X is in that domain of the inverse. Okay, I am going to stop the video here, and when I come back in the next video, I'm going to do some specific examples of if we have a formula for our function, how do we find a formula for the inverse?